Awesome. Hello, everyone. Welcome to another series of the NL seminar. It's a pleasure to have today Ruiqi Zhong from UC Berkeley. He's advised by Professor Dan Klein and Jacob Steinhardt, and he mainly works on NLP and AI Alignment. His research aims to enable humans to effectively supervise AI systems on tasks where the ground truth is hard to obtain. He's told us that he reads about epistemology, thank you, and labor economy in his spare time. You can already tell how little I know about it. So it's a great pleasure to have him today. His talk will be on getting AI to do things I can't. I think the title is already very intriguing. I'm super excited to hear about what he has to share today. So without further ado, let's get the stage to
All right, so thanks for having me here. Today I'm going to talk about a topic that I am particularly excited about, getting AI to do things that I can't. Before we dive into the technical detail, let's look at the NLP research landscape on a very high level. So there are two broad categories of tasks. There's the things that humans are good at, and there's the things that machines are good at. Typically, when we propose new NLP tasks, we take the intersection of the two, which is called automation. So in these cases, we collect a bunch of human labels, we ask AI systems to mimic human demonstrations, and we evaluate AI systems based on whether they agree with human label. So this looks great, and we can just apply imitation learning framework to it. However, for many things that, for example, I care about, humans might not be necessarily good at them. So it would be great if we can augment humans with AI systems. So here's my wish list. I would love AI systems to be able to discover patterns in data and explain to me in natural language. I want AI systems to write a program for me that I might not even directly understand. I want AI systems to help me predict the future, and I want AI systems to help me run and design experiments. So it would be great if we can do that, but it is unclear how we're going to supervise AI systems for this, because the traditional imitation learning paradigm will not be very suitable. Because if humans are not good at it, we should not ask AI systems to mimic humans. So the focus of today's talk will be, how can we supervise AI systems even when we struggle to verify that it is correct? Okay, so unfortunately, I do not have a general solution, but I do have reasonable methods to tackle the first two items on my wish list. I'm going to talk about two tasks. For the first task, I'm going to give AI system two large corpora. So for example, patient feedback for drug A and patient feedback for drug B. We are going to ask the AI system to read the two large corpora and describe their difference in natural language. So for example, patients more often have strong feelings of paranoid after taking drug A. For the second task I'm going to talk about, we're going to give AI systems a natural language query. And then we are going to ask AI systems to produce a very complex SQL program. And in particular, we are interested in a setup where we enable a person who do not understand SQL to be able to supervise AI systems to write complex SQL programs. Well, imitation learning will probably not be the great idea here, because even experts are far from perfect at doing these tasks. Experts might make a lot of mistakes in writing SQL programs, or might not discover all of the patterns in the large amount of data. But by the end of the talk, I will show that it is possible to build AI systems that can discover patterns in data that even experts have not noticed before, and enable people who do not understand SQL to write SQL as accurate as database experts, and additionally help us identify that actually in one of the most popular semantic parsing data set, there are 25% of the annotation mistake. The method that we will develop today, I will call it propose and reduce. At the top of the screen, we are going to, this is an imitation learning framework that everyone is familiar with, where the human supervisor will write the full output of the AI system. And at the bottom of the screen is going to be our approach, where we are going to ask humans to indirectly verify the output on easier problems. It requires two conceptual advances to get from the top, which is imitation learning, to the bottom, which is our approach. The first conceptual advance has already happened, which is the switch from imitation learning to learning from human preferences. So for example, instead of asking humans to write the full output to supervise a model, right now we can ask AI system to propose multiple different outputs and then ask humans which one of the output is correct. So for example, instead of writing the full dialogue response or writing the full explanation or the full summary, we can ask human to pick which one of the dialogue response, explanation, or summary is the best for them. This makes it much easier for human to supervise AI systems for similar reasons to P not equal to NP. Well, we don't know yet, but P versus NP. The analogy goes like, there are a lot of hard problems that it is hard to directly generate a solution, but once someone provides you a solution, it is much easier for you to verify that it is correct. So that is the first step proposed. However, although it seems that we have reduced the problem to something much simpler, we are not there yet for a more complex task. Because for a lot of things that we care about, it is still hard for humans to even verify the ground truth. So for example, how do you enable a person who do not understand SQL to verify that the SQL provided by a model is correct? How do you verify that the corpus level description is correct if you have to read through two large corpora? So here, this talk will contribute something more, which is called reduce. So instead of asking humans to directly verify that the output is correct, we can make it simpler for humans by reducing the problem to something easier, and then humans only need to indirectly verify that the output is correct. So instead of asking humans to, or say non-experts to pick which one of the source code is correct, we can ask them to run the test cases and then tell me which one of the test case output is correct. Instead of asking them which one of the description is correct for the two large corpora, it might be simpler for them to look at the description on individual samples. And instead of asking them which one of the book summary is correct, it might be easier to ask them to look at some parts of the summary and then recursively combine each of the individual summaries that is easier to verify. Cool. So that's the overall description of our framework, propose and reduce. And next, I'm going to talk about the two tasks, discovering and describing distributional differences, and supervising code generation models with non-programmers. And at the end, I'll talk about some future work and some of my hot takes. Okay, so the first task, discovering and describing distributional differences. This is based on these three papers. This is a fairly new task, so let me introduce the setup. The input to this task will contain three things. The first thing is your research content. So for example, I am an educator. I want to understand how students write essays differently across different schools. And then the rest of the two part is going to be a pair of corpora, corpus A and corpus B. Corpus A, student essays from school A, and corpus B, student essays from school B. So given the research context and two large corpora, we want the AI system to produce a natural language description of how they're different. So for example, student essays from school A uses numbers and statistics more often. So why do we care about this task? It turns out that a lot of interesting problems can be reduced to this task. For example, if you're interested in distribution shift, where there is a gap between your training distribution and test distribution, then you can set the actual user's query at deployment time as one corpus, your training data as another corpus, and then you can try to ask the system to describe the difference between them. So our system might discover that the user's query contains more slang compared to the training data. If you're a political scientist, you might be interested in different political stances of different people, and then you can compare Obama's speech versus Trump's speech. And if you're interested in studying how humans, or say people who are not working in AI, to perceive the machine-generated text, you can set one one corpus to be texts that are considered to be human-written and texts that are considered to be machine-generated, and compare the differences. So there are many more applications there. I won't go into the detail of it, but just to give you an idea of how many different cases we can apply this thing for. So this seems to be an interesting and important task. However, it is quite difficult. What typically happens is that you'll give AI systems 17K samples for corpus A, 17K samples for corpus B, and then you ask it to tell their difference. It seems to be really hard for humans because humans don't really have a lot of time to scroll through all of the samples from the two corpora, and it would be great if we can supervise AI systems to assist humans to do that. Okay, so how are we going to supervise AI systems to do that? I want to take a step back and introduce some formal notation. So we are given the research context. I want to understand students writing essays differently across different schools. And the corpus A, we'll call it distribution A of the text. And for the corpus B, we're going to call it the distribution B of the text. Given the research context to distribution of text, we're going to generate a natural language description, which is underlined, which we call S, that reflects the difference between DA and DB. And I want to specifically note that we are mining correlational features rather than causal features. So for example, if our system says more samples from corpus A use numbers and statistics, it does not imply that if you go to school A, then the teachers will teach you to use more numbers and statistics. And it also does not imply that if you use numbers and statistics, you are more likely to be admitted by school A. Anything could happen. We are only interested in correlation structures in this talk. And we notice that S, which is the output of the AI system, is actually pretty hard to label for humans because humans do not have time to read through the two corpora. So we're going to apply our method, which is called propose and reduce. And let's first look at the propose step. Instead of asking humans to write the full description themselves, we're first just going to ask large language models to propose many different candidate descriptions. So here is a prompt that we use. We first prompt the language model a subset of samples from distribution A, a subset of samples from distribution B, and then tell it about our research context. And then we're going to ask it, okay, so here are some examples. Tell me a list of hypotheses about how they can be different. And then large language models will be able to propose multiple different candidates. So for example, is offensive in tone, uses more statistics, et cetera, and et cetera. We're going to repeat this process by resampling different samples from DA and DB, and then repeat this process for 60 times to generate a large number of description. And finally, we have a large amount of candidate, and what we need humans to do then is just to verify which candidate best discriminates the two corpora. So again, we are going to ask AI systems to propose multiple different candidates, and then we want humans to be able to verify which one of them is correct. However, as we alluded before, it is still difficult to verify whether a description is correct on the entire two corpora of DA and DB. So instead, we reduce it to something easier, which is we ask humans to verify whether the description is valid on individual samples from DA and DB, and then later combine the individual judgments later. Specifically, the way we operationalize this is as follows. So let's say we have a description S, samples from DA uses more numbers and statistics. We want to verify whether it is correct or not. What we do here is we take two samples from DA and DB, but we don't explicitly say whether DI is DA or DB. We take two samples, and then we give the two samples to another human. Oh, by the way, this is the second author of the paper. We give the two samples to that human, and then after looking at the two samples and the description, the human classifier would say, okay, I think XA is from DA and XJ is from DB because XI uses numbers and statistics. And then we can repeat this process for a lot of different times and then calculate how accurately can human use the S to determine whether X or xj is coming from DA or DB. So this is how we're going to operationalize this. So just to reiterate, the loss of the description is how accurately it can enable a human to tell whether a sample is coming from DA and DB. However, we are running into some trouble because this requires a human in the loop, and we are going to ask humans to do this for 100 times. And in fact, we operationalize this in our paper. It took us $10 to even evaluate one single description. So this doesn't seem to be ideal. So there's one more step we could do there, which is instead of asking human to classify whether xi or xj is coming from DA and DB using the description, we can swap it with a question answering model. And we're just going to ask, okay, so among xi and xj, which one of them satisfy more about the property that it uses numbers and statistics? And we can approximate the loss by saying how accurately a machine can use as to guess a membership of X, which is whether X is coming from DA and DB. And notice that we have a prime here for the loss, just to indicate that it is an approximation of the ground truth loss function, which is based on human judgment. If we do this with machines, this becomes much cheaper to calculate the error rate of a model. Okay, so that's the overall method. Just to recap, we have the recipe of propose and reduce. The method is we're going to first propose multiple different candidate descriptions with GPT-3 or potentially GPT-4 in the recent days. We reduce the verification problems to something simpler that individual humans can perform. So for example, examining individual samples. And finally, we make the verification more efficient by simulating humans with machines.
Sorry, quick question, just to make sure I understand correctly. How do you train the machine classifier yourself? So
yeah, so the machine classifier can be done in two ways. First of all, you can do it with zero-shot or few-shot prompting. And secondly, in our paper, we actually did collect some data on human judgment, and then we train a model to simulate human judgment.
Did you filter in some way like from the descriptions that you got from GPT-3, or did you just test all of them?
Yeah, I tested all of them.
Oh, I see.
Well, we actually only consider 60 of them, so it's actually not a great number to consider, but it is still like one of the main computational bottleneck for this project.
So wait, you are saying that you sample two subsets, and then for each pair of subsets, you get 60 descriptions? And then you do multiple subsets.
Okay, so in the first version of the paper we wrote, for each subset of samples, we just get one description, and then we try different subset of the samples until we get 60. And then for more advanced models like GPT 3.5, we just directly say, can you come up with a list of hypotheses, and it might be able to come up with 5, and then we just repeat this step for like 12 times, and then we obtain 60.
So we have a question from the audience. Zihao is asking, what if neither xi or xj has numbers in it? How does the machine make a decision in that case?
Yeah. So very good question. So in the first paper that we wrote, we defined it to be the model should answer no, which is compared to the second sentence, the first sentence does not necessarily use more statistics or numbers. And because if you swap the first sentence and the second sentence, either way, it will give you no, then it's actually, it implies that the description is actually not a good discriminative description, if that makes sense. Great. Cool. All right, so.
I just have one question, sorry.
Sure.
Are there cases or hypotheses where reducing to samples just wouldn't work, theoretically speaking, or like, for example, here you have this, you try to verify whether one sample or one corpora has more numbers than others. maybe if we look at individual samples, we can, like, independently, we can come up with a conclusion, but what if like there are other things that we want to verify that cannot be like the sum of our conclusions based on different independent samples?
Oh, cool. Okay. So yeah, that's a great question. So for some, actually, you can sum the conclusion for an individual distribution, individual samples from the distribution. But indeed, there are actually conclusions that you cannot verify by individual samples. For example, how large is the variance of the length of the sentences in the distribution, or like any things that requires some higher order statistics. Our method was actually not able to deal with that. So I guess this would be probably some of the future work. Yeah.
Oh, okay. Thank you.
Cool. All right. So let me continue this. And okay, so I just did a recap of the method, and now let's actually evaluate our AI systems. The victory condition there will be after the reduced verification, which is the blue one, it should perform better than we simply take a random sample from the language model's proposal, which is a purple proposed without verification. So the victory condition is blue is larger than purple. So here is the toy benchmark that we used. We try to, so there are 54 binary text classification tasks, and we try to recover the description for them using our system. So specifically, let's say there is a binary classification task, and there are samples with label 1 and samples with label 0, and there are distribution A and distribution B. We want the AI systems to be able to look at distribution A, distribution B, and then come up with a natural language description of what samples have label 1, which is the task definition of this 54 binary text classification task. And so, so here is the result. Suppose that you just take a random description from the proposer. The accuracy is only 7%. But suppose that you use a description after reduced verification, the accuracy would improve to 31%. And we evaluate the quote-unquote accuracy by manually checking whether the machine-generated description is semantically similar to the original task description.
Sorry, quick question. So do you consider one gold description for each set of?
Yes, so in this setup, we only consider one gold description, but we do blinded manual evaluation for checking whether the gold description is semantically the same to GPT-3 generated description, because otherwise, like there are a lot of descriptions that are semantically the same, but stylistically different.
Also, like beyond semantically equivalent description, do you also look for descriptions that are correlated? Like, for example.
Oh yeah, definitely. So we actually did look at the correlation, and if you look at highly correlated descriptions, the numbers are much higher. But but here I'm only showing the more rigorous rigid evaluation. Yep. Cool. Okay, so this is the result of the benchmark, but it doesn't seem to be that exciting because it's not actual application that we care about. So we put it into practice, and here are some of the examples. The first example that I'm going to show you is dataset misunderstanding. So there is a dataset actually in our benchmark that is called SUBJ, which is Subjectivity Analysis Dataset. And at least more than 4 papers use this dataset to test language models' capability to classify whether a text is subjective or objective. So we feed the 2 corpora, the quote-unquote objective text and subjective text to the AI system. The AI system produces a natural language description as a plot summary of a field. So back then we were actually super confused because this just doesn't seem to be correlated with the dataset itself. But it turns out that if we dig deeper into how the dataset was collected, it says to gather subjective sentences, we collected 5,000 movie reviews, and to obtain mostly objective data, we took 5,000 sentences from plot summaries. So to some extent, it actually discovered something that we as authors didn't even notice before, and we contacted the before previous paper whether they actually noticed this sentence when they used the dataset, and all of them said no. You can also use it for describing distributional shift. So we are applying this to describing distributional shift between natural language inference data set. So SNLI and MNLI are two different natural language inference data set. We feed it to the system, and our model says SNLI involves more physical activities such as walking, playing, climbing, or biking. One possible explanation for this is that SNLI contains sentence-based picture portrayal, while MNLI has multiple genres. So for example, speech or fiction. So in that sense, it sort of makes sense because you might see more physical activity in some picture-based corpora. You can also use it to analyze model errors. So for example, we might want to answer the question, what inputs cause a model to fail? And we have a task of zero-shot classify whether an argument supports a claim or not. We construct the two corpora in this way. There are a set of sentences or a set of inputs where model A misclassifies the label as support, while the ground truth is actually undermined. And there's model B, which misclassifies the label as support where the ground truth was actually undermined. If we compare the two, our model finds that corpus A contain more language that are positive or uplifting. So one potential explanation for this is that model A might have misunderstood support in the instruction as a sentiment label rather than a logical label. So I won't be able to get into more applications here, but so far we have presented 3 applications in machine learning, and there are probably much more. So for example, you can use it to debug dataset shortcuts, label text clusters, explain what inputs are activating a neuron or not, describe principal components, compare language models generation. So for example, how does the generation from ChatGPT different from Claude, which is from Anthropic? You can also try to explain human preference data set, etc. So this is restricted to machine learning applications. And if you look at it more, there are many social science, health, humanities, and business applications. And in our most recent paper, we collected 600 similar problems, and feel free to check it out if you're interested. So here is the main takeaways for task 1. For the setup, we want to describe distributional differences. It's a hard task that humans might not be able to do themselves and also find it challenging to verify. And in terms of the method, we first propose a description with GPT-3, and then we reduce the verification problem to something easier for humans by asking them to verify individual samples. And finally, we make verification more efficient with machine simulation. And finally, it is able to discover insights even human experts did not notice. Okay, any clarification questions?
I actually have a question. So I'm wondering if this can be extended to find anomalies in the data set, and how can we set up a problem to find such cases?
Yeah, so I guess, so suppose that you want to stick with this framework, then you would set the data points that are likely to be anomaly and then compare it to the rest of the data sets. Although this method cannot detect which data points are looking like anomaly. So you have to first come up with the anomaly data points first. Does that make sense?
Yeah, sure. So I guess maybe when you're sampling the data points, you can do some tricks there, even for your method to discover these patterns more easily. And I guess that kind of ties to the anomaly detection work as well.
Yeah. Yeah, I think that's a pretty good direction. Okay, cool. So I will move on to the second application, which is supervising code generation models with non-programmers. And this is based on the 2 papers that I've written before. So here's a task setup. Given the natural language question, how old is the youngest person from department A? We want to generate a SQL program. So for example, select minimal age from people where department equals A. We want to generate a large number of pair of natural language plus SQL programs to supervise AI systems. However, this part is actually pretty hard to annotate because you have to recruit a lot of non-programmers to supervise models to write SQL. And the focus of this project is how do we enable people who don't understand SQL to supervise AI systems to write SQL programs. So again, remember our two-stage framework, which is called propose and reduce. For the propose step, we are going to have a natural language question, and then we ask Codex to generate 32 different SQL candidates, and each of them are being associated with some kind of probabilities. And then what we need non-experts to do there is just to verify which one of the candidates is correct. However, it is still going to be very challenging for a non-expert. So for this particular case, it's actually really easy because there is a direct correspondence between minimum age and youngest, and there is department equals A aligned with department A. So you might think that this is an easy problem, but it turns out that it is not. Because typically what's happening in this data set is that we are going to ask people who do not understand SQL to pick which one of the SQL program is correct out of 16 different SQL candidates that is as complex as this. And then we're going to ask them to choose which one of them is correct. So this seems to be pretty challenging for people who do not understand SQL. So we'll have to reduce it to something easier for people who, easier for them. So here we make the reduction. So instead of asking them to verify that a program is correct, we reduce it to something like ask them to verify that a program has the right input-output behavior on example test cases. Concretely speaking, we operationalize this in this way. So let's say we have a natural language question: how old is the youngest person from department A? We have 3 different SQL programs, and just for convenience, let's just imagine that there is a magical database that is coming out of nowhere. And then we're going to use this database to help people who don't understand SQL to tell us which one of the SQL program is correct. So we're going to show the database and the question to people who don't understand SQL. And then by looking at this table and the question, they will say, okay, 23 seems to be the right answer. And then we're also going to execute all of the 3 SQL candidates, and then execute them on the database, and the program will give different output for that database. So for example, Kathy, 28, 23. Then we'll be able to check whether the answers by the SQL programs will be different from the answers that people who don't understand SQL get. As a result, we'll be able to say, okay, so the first 2 answers is wrong, so probably the first 2 SQL programs are also wrong. So in this way, you'll be able to figure out that the third SQL program is the right answer. However, there's one important detail that we haven't talked about yet, which is how do we even pick such a database, because we assume that it is coming out of nowhere. So next, I'm going to talk about how we're going to generate the database. And specifically, we want to use the principle of we want to maximize the bits of supervision with minimal human effort. And concretely speaking, we're going to say that the size of the database needs to be small, while the information gain of the database needs to be large. Concretely speaking, suppose that we give such a database, which has 1,000 rows, to people who don't understand SQL. It might take them like 2 hours to figure out what is the answer, because they have to check individual rows. This is not good. So we'll say that the size of the database needs to be small. We notice that size will be a function that maps from a database to a real number. And okay, so let's look at this second example. So this database has a really small size, but it's actually not very ideal, because if we feed this database to the 2 SQL program and then ask the annotators to answer, all of them will deliver the same answer, which is 23. This database is not informative at all, because all of the SQL program and the non-experts will give you the same answer, and as a result, you will not be able to eliminate any of the SQL program. So to formalize this, we actually want the answer to be as diverse as possible. And here is a formal diagram. So we have probabilities, which is 1/3 for each of the 3 SQL candidates, and we want the answer to be as diverse as possible. And then we calculate the entropy of the answer. So for example, which is 0.92 bit. As a result, we'll be able to say that this database has an information gain of 0.92 bit. And again, notice that information gain is another function that maps from database to a real number. And also the information gain function is dependent on the distribution of SQL program that you are beginning with. So far, we have listed two functions of the database, and then this just becomes an optimization problem where we want to optimize the database information gain under certain size constraint. Because of the time limit, I won't be able to go into the technical details of how we are going to do this. But on a very high level, we first use fuzzing to generate a large number of databases with large information gain, and then we drop rows iteratively to decrease the size such that it can match the size constraint. And sometimes one round of database interaction will not be able to reduce the number of candidates to 1. So we can repeat this for multiple different times until we are satisfied with the remaining entropy. So here is a recap of the method. So for the method, we are going to propose SQL programs with codex. We are going to ask non-experts which one of them is correct by reducing the verification problems to just examining answers on databases. And finally, we are going to make the verification more efficient by making databases small and informative. And here is our victory condition. So after reduced verification with non-experts, it needs to perform better than the raw large language model, which proposed SQL candidate, and then we take the most confident one. So again, we want blue to be better than the purple. Okay, so now we're going to go to the experimental setup. And just to recap, we're going to first have a natural language question, and then we have a bunch of SQL programs. And then we take the top one, which is the most confident predictions, as a purple one. And then we are going to make some interactions with the non-experts, and then it will be left with the blue one, which is what we call the non-expert annotation, and we want blue to be better than purple. Then it comes a question like, what is the ground truth? How should we establish the ground truth to compare the two? So what we did in this paper is, so first of all, there was actually prior expert annotations by previous database experts, and which is what we will label as red. And then to establish the gold standard, we did extra work. The authors used our system to help annotation. We also checked the SQL directly. We compared with previous annotations, and whenever there's ambiguities, we always favor the previous annotation to prevent bias against the previous system. And also we discussed with the previous annotators about what is the best annotation. So this is how we establish the gold standard. And now let's look at the result. The codex top one accuracy is 59, so it's reasonable but not great. So after interacting with non-expert annotation, the accuracy is improving by 16%. So blue indeed outperforms the purple, indicating that our approach is effective, but of course still has a lot of room for improvement. And then actually let's look at what the previous expert did. Previous expert only also has 75%. So you might wonder, what are the kind of examples that the previous expert got wrong? So remember this complex SQL programs before, where you have find the first name of students who have both cat and dog cats, and then you have the annotation from our system, which is correct. And then actually one of the previous experts wrote something that is semantically equivalent to this, which is wrong. I will first tell you on a very high level how they're different. The blue SQL program, which is correct, will find the students who have cat, find the students who have dog, takes the intersection, and then find their first name. The expert-written SQL program, what they will do, which is wrong, will be they find the first name of students who have cat, find the first name of students who have dogs, and then takes the intersection of the two. So if you don't think carefully, they look pretty similar, but if you look at one actual database, you immediately realize that the expert annotation is wrong. So suppose if you follow the logic of expert, here will be a database where there's two students, Alex Pan has a cat, and Alex Wei has a dog. Suppose that you follow the logic of the expert, you'll say, okay, there is a student with first name Alex has a cat, there is a student with first name Alex has a dog. And if you take the intersection of the two, you'll conclude that Alex has both cat and dog pets, which is actually wrong. So there are a lot of such subtle mistakes in the original spider data set, and our system is actually able to tease that out. So here are the takeaways for the second task. So the setup is that we want to enable people who do not understand SQL to label complex SQL programs. The method that we use is we are first going to propose different SQL programs with codecs, and then we're going to reduce the verification problem to examining input-output examples. And finally, we'll make the verification more efficient by maximizing information gain under size constraint. Any clarification questions?
So is the motivation or the use case for this task to have, I guess, even mechanical Turk workers who know nothing about SQL programs to like verify outputs from large language models and their program synthesis, and thus, more efficiently, price efficiently, or cost efficiently improve on these models?
Mm-hmm. Yeah, so that was one of the applications that we were originally thinking when we were still working with the first version of the codex, where the SQL program is still not that great. But right now the models are becoming much better. So the newer applications you can think about is, suppose that you have a medical database, and then you don't have people who both understand the medical domain knowledge about understanding the specific database, and also know how to write SQL. So you can use this method to supervise AI systems to write SQL programs in that particular domain. And I also believe that the general principle of indirectly verifying a program is correct, can be applied to many other programming languages that is more complicated.
I have a question. So I really like the idea of this optimization and using this info gain. I thought that was really cool. I'm wondering in cases that the model would randomly generate the correct answer while the code is not correct. Do you think you can make this optimization more smart, or the info gain might capture these cases, but do you think we can impose other objectives that can control for this randomness in the answer?
Other objectives to control the randomness in the answer. Okay, so I guess there are a few things we could do there. So because generation is always harder than verification, there are some other things we could do. So for example, there is some other reward model or verification model that can directly reject some of the random generation. So one way to think about this is you're going to ask a language model to brainstorm a couple of SQL programs, and then you're going to ask a verifier to verify which one of the program is correct. So that could be one additional objective where you try to optimize against a learned verification model. And I guess also in the future, so right now we are using humans to look at the database and the question and then produce the answer. And in the future, you might actually just directly ask GPT-4, here's the database, here is the question, and then what is likely to be the answer. And then you can encapsulate all of the interaction, to put all of the, enable all of the interaction just with a model, and then further reduce the human effort. And then like the model's implementation process will be more like, it will write multiple programs and it will debug itself by running the program on multiple different test cases. And that's probably one more thing you could do in the future.
Thank you. Those are really cool ideas. Thank you.
Cool. Yeah. Okay. All right. So next, I'm going to talk about. Oh, okay. Sorry. One more thing. Yes. So using our system, you can discover that the previous data set has at least 25 annotation errors, which I actually didn't know before. All right. So let's talk about future work. Future work. First of all, it will be two parts. The first part is technical discussion around the new research paradigm, which is called Scalable Oversight. And secondly, I want to have some broad discussion about the high-level picture and somewhat hot takes, and which is meant to be speculative and provocative. So hopefully we can have a lot of fun there. Okay, so the research paradigm of scalable oversight. We want AI systems to augment humans, and instead of just doing things that humans are already good at. And suppose that we want to do that, then one of the main challenge is actually for humans to oversee those AI systems whether they are doing things correctly. In this talk, we developed a two-stage recipe, which is propose and reduce, and then we would make indirect supervision more efficient by simulating human verification with a learned model, and then maximize a bit of supervision with minimal human effort. In terms of future work, you can apply it to many more different tasks. So for example, for complex mathematical reasoning, it might be pretty hard to directly verify the answer, but perhaps you can verify the answer on individual decomposed steps. For machine translation, for example, instead of asking humans to directly verify the whole output, you might be able to just ask them to verify some uncertain key phrases. And finally, I think it will be worthwhile to develop a task-agnostic oversight framework where we don't have to have a different reduction scheme for each individual task, because right now GPT-3 or GPT-4 are pretty general purpose models, and the users will use it in many different ways, and we don't want to have a reduction scheme for each individual use cases. So this is a new research paradigm. However, there are some evaluation challenges. The key reason is that right now we don't have ground truth human labels, and it becomes tricky to evaluate. So one way to do this is that you can establish the ground truth with a large or infinite budget. So for example, the budget here can include whether you are recruiting experts to help you determine the ground truth, and then they might spend like 2 hours or even a year just to determine one output of the AI system. In such a way, you can establish a very high quality ground truth, and then you can compare that ground truth to your proposed method, which only has a small oversight budget. So for example, the small oversight budget might be you can only recruit people who do not understand SQL, and then you try to compare it with the ground truth where there are a lot of expert SQL programmers looking at the output, and then they discuss whenever they disagree. For further reading, I would recommend the paper Measuring Progress on Scalable Oversight for Large Language Models by Sam Bowman, who for this year is working at Anthropic. And again, this is a pretty young research field. There are a lot of conceptual challenges and opportunities, and I would love to discuss after the talk. Okay, so now I'm going to talk about the broader landscape of this line of work. I would argue that oversight is going to be a relatively impactful research direction, but also is going to be very challenging. This research direction is going to be challenging for 2 reasons. First of all, currently we already observe that it can be challenging, and then in the long run, we will observe that there's a trend that is becoming more and more challenging. For the current situation, if you look at ChatGPT or Copilot, they can very frequently produce highly plausible program stories or explanations. And it is challenging for humans to identify that it has mistakes. This is one example from the helpful, honest, and harmless paper from Anthropic. And here, the human has a question: can you help me understand how US presidential election works? And the better response here compared to the worst response is that, I'm sorry, I don't know the answer, perhaps you can Google it. The worst response is actually worse because it has a lot of factual mistakes. So for example, saying that there are currently 270 electors in all, and you have to win at least 250 electors to win the election, which is definitely not true. But overall, it sounds really plausible for people who do not understand US presidential election, or people who are just being careless when they are trying to decide which one of the response they prefer. And initially, actually, I asked Anthropic people what are the actual mistakes in the worst response when I provided the paper draft feedback. And they say, okay, so there are a bunch of factual mistakes like this, this, and this. And I said, there's actually one more that you didn't discover, which is I did a Google search. So back then, the language model didn't have a plugin, but so it shouldn't say I did a Google search, which is hallucinating. Okay, and suppose that, and so it is already challenging now, and in the long run, you should be expecting that it is increasingly challenging because AI systems predictably acquire unpredictable behaviors. So in the past, in 2019, we were surprised that GPT-2 can improve downstream performance on a lot of different tasks. And then when you scale it up, we didn't expect in context learning behaviors, instruction following behaviors, chain of thoughts behaviors. And maybe you're right now get used to that. And if you look at GP4, there's something even more crazy, which is they did some study and then say we query GP4 3 times, and they ask it to draw a unicorn in Tixi. And then you get this pretty cute unicorns. And this, at least I didn't expect this to come. And given that we are being surprised historically, we should expect more surprise to come in terms of AI capability. And on the other hand, humans will grant greater powers to AI systems. And so, for example, if you look at this, which is the plugin for ChatGPT, it is being plugged into many different apps and allow language models to take actions in the real world. So right now, it is only limited to the Git operation for a website, but you can imagine that as the landscape of business become more competitive, the safety constraint might loosen up and allow large language models to actually post stuff online. And although AI systems are being more and more incredible, humans as biological species actually do not evolve that fast. So why do we want scalable oversight? Why do we want humans to be able to oversee AI systems in a more scalable way, scalable with respect to AI capability and also the complexity of the task? So to summarize, human as a species with most slowly increasing oversight ability is granting drastically improving and unpredictable machine learning systems, an increasing amount of autonomy and resources to take actions and perform increasingly complex tasks at a planetary scale. So I would say that there is urgent needs to empower humans to effectively oversee these AI systems. Okay, so that's the end of the talk. I would like to thank all of my collaborators, my faculty mentors, and my undergrad mentees for contributing to this research. And I would love to take questions, and I would love to prioritize technical questions first, and then later we can get to the conceptual questions because that usually are more controversial and takes more back and forth. Cool. All right, so technical questions? Oh, okay.
I think we had a lot of technical questions throughout the talk, so that's why I think it would be more interesting and best use of our time to quickly move on to the more interesting hot takes. So I think, Peter, if you can stop the recording now, that would be great.